So what we're going to talk about today, like right now, basically the relationships between different parameters that can characterize a gas, namely amount, temperature, volume, and pressure. And the very first relationship is between pressure and volume that is governed by the Boyle's law. Okay? Boyle's law can be essentially formulated like this. If the temperature and the amount of gas are constant, then with increased volume, the pressure decreases and vice versa. Sounds fair? I will demonstrate it. And it is fairly intuitive. So if you look at this illustration here, for now I would ignore that, the numbers. If you look at the left image with a volume 1, this volume is greater than the volume 2, right? So we're essentially decreasing the volume. But by decreasing the volume, we effectively increase the concentration of particles in that same volume. So they bump into the walls of the container more often. Does that make sense? Okay? Basically, if I will try to, like, you all feel pretty comfortable in this room, but if I will try to squeeze you all in like one person elevator, that immediately becomes, crowded. So basically, this is what we need to highlight here. Temperature is constant, the amount is constant, and the product of pressure multiplied by volume then remains constant. Here is the Boyle's law. Now, and it works both ways, okay? So, volume decreases, pressure increases. But you also can establish the opposite relationship. If the pressure increases, okay, the volume has to decrease. So, these are different illustrations to this concept. In a system where temperature is the constant and the amount of gas is constant, PV is constant as well. So here's the thing. This is really, like, some of you have taken NP2 already. Some of you, maybe, I don't know, will take an NP2. But the process of inhalation is essentially governed by the Boyle's law. When you inhale, your diaphragm goes down, your rib cage goes up because of the intercostal muscles, and effectively the volume of your rib cage, V2, becomes greater, it increases. Well, if V2, the volume when you inhale, goes up, then the pressure inside your lungs has to go down. As the pressure inside your lungs decreases, the air flows into the lungs. And exhalation, which is a passive process, you basically relax all those muscles. Your diaphragm goes up, your rib cage goes down and inward, okay? The volume decreases, the pressure increases. Okay? Reasonable? Awesome. So, simple calculations. The only thing that I can think of that can mess up your calculations during the exam when you forget that the units may be different. Always pay attention to units. This is not the case, okay? So what we have is the pressure and the volume. So we can say that 12 liters multiplied by 600 millimeters of mercury is the same as new volume, right, multiplied by X millimeters of mercury. Making sense? Go on.
12.0 liters times 600, is that the same equation as like the PV?
Yes, exactly, yes. So, in a nutshell, clear, look at this. So it's P1 multiplied by V1 equals, well, actually the opposite. Sorry. Okay, this is P1 and P1, and this is V2 and P2 that we try to find. And it's going to be 200 millimeters of mercury. You can do the math yourself. Does that make sense to everybody? All right? Okay, cool. So, same story to illustrate. So it's a V1 and it's a P1. This is P2, so we can find V2, right? So we can say that P1 multiplied by V1 equals P2 multiplied by V2. Therefore, V2 equals P1 V1 divided by V2. You can do it entirely in numbers. You can work. Any questions on this calculation that I'm running? Okay. This is what we're trying to find. So new volume is V2. Yes. My bad. Thank you. Yes, P2, of course. So, in other words, we need to multiply 850 millimeters of mercury by 120 mils. Okay? And divide by 425 millimeters of mercury. Always check the units, okay? And this is going to be 240 ml. Making sense? Excellent. Now, when you're going to be reading the questions, if the question asks, okay, blah, blah, let's say this question, what is the new volume in liters? The answer is not 240, you need to convert it in liters, okay? So that's Boyle's. Charles' law governs the relationship between the temperature and the volume. Okay? This is a Charles' law in a nutshell. You are familiar. What I like about these laws, they make sense. You encounter them in your everyday life. Okay? Here's what I'm talking about. This is the volume at the beginning at 200 Kelvin. You start heating it up. When you increase the temperature of the gas, what happens to the velocity of collisions? It increases. What happens to the frequency? It increases as well. More frequent and more powerful collisions constitute the increased pressure, right? But we say that the pressure is constant. We do not restrict the movement of that plunger. So this plunger will go up, increasing the volume while maintaining the same pressure. Bless you. The best example, if in the summer you will pump the tires on your car while it is parked, and then it's like super hot, and you're gonna drive on the road, and you measure. Well, it's not. Well, the tire can explode because it tries to increase its volume. Does that make sense?
So this is the concept of like a helium balloon when it's cold outside, it starts to like contract.
Absolutely, exactly the same. So basically, the greater pressures in moles, when the temperature increases, the volume increases. Okay? All makes sense. So let's say we have a balloon here. So this is your volume 1 and temperature 1. Okay, remember this is the relationship. V1, V over T. Okay? So what's going to happen if the pressure drops to 0 degrees Celsius? Okay, what's the new volume? So this is T2 and this is V2. Now I'm going to ask you something. Can you just tell me what numbers I need to write? Just literally straight up tell me. 700, hold on, I will remind you that V1 over T1 equals V2 versus T2. So let's convert it into the number game. Tell me, I'm not going to comment, just tell me what I need to write. Okay. Okay. Oh, shit. Can you divide by 0? What are we going to do? Yes. This is one of the most common things to get mistaken. You have to convert it in Kelvin. So 21 degrees Celsius. What do you need to do to convert Celsius in Kelvin? Add 273. Okay, right? So 273 plus 21 gives you 294 Kelvin. I want to remind everybody that the temperature in Kelvin is the same as the temperature in Celsius plus 273. Okay? So instead of 0, it's going to be 273 K, and that's going to be V2. Does that make sense to everybody?
Even though the 21 Celsius is the T1.
Yes.
That you're adding that Kelvin from that degree Celsius, because you technically the 0.
Okay, so the only temperature scale that we are allowed to use with these laws is the Kelvin scale. Even though the temperature is given to us in Celsius, we must convert it into Kelvin. And this is the way you do it. So I can technically give you temperature in whatever units. You just need to convert those units to Kelvin, and then you can do calculations. I don't know if, am I answering your question? Okay, good. Now, obviously, you can do these calculations, okay? It's going to be slightly less than 785. This is another important thing to remember. Hear me out. So this means that if the temperature decreases, the volume decreases as well. Does that make sense? So if you do the calculations and this answer is lower than 785, it makes sense. But if it's greater, something went wrong with the calculations. Does that make sense to you? Okay. Same here. Now you know what do we need to do? So this is V1, this is T1, this is V2. So write down this. V1 over T1 equals V2 over T2. Okay? Good? So that means 420 over, what is the number? Huh? 291 Kelvin. Don't believe? No. You're right. 291. And here, what should I do? T2 and 420 on top. Okay? Wait. Am I wrong? Oh, 640. I'm sorry. I misread this. So, I believe that you can calculate it. First of all, will T2 be more or less? More. So, temperature number 2 has to be more than 291 Kelvin. Correct? We can try to calculate it, stating that it's going to be 640 ml multiplied by 291 Kelvin divided by 420 ml. So far, do you follow my train of thought? Okay. We can divide by 20, so it's 21, it's 32. So give or take 1.5 times more. Am I making sense? So it's probably going to be about 435 or something Kelvin. Am I right? 443, not bad for winging it. And then to convert it to Celsius, what do you need?
Subtract 273.
Yes. So 443 minus 170 equals, 273 equals 170. Fairly reasonable, right? Okay. Go on.
I'm sorry. Where did you get the 32 and the 20?
Math, it's okay. Okay, cool. Gay-Lussac's law. So temperature increases, pressure increases. Am I making sense? It's that is it. So basically, what we state. So this is the situation with a car tire that explodes. Am I making sense? If you overpump it and then drive in the heat. Because the pressure increases so much, breaks it in pieces. Making sense to you all? Okay. So this is the relationships. Okay, we can rewrite it this way. P over T is constant if the amount is the same and the volume is the same. All good? So, P versus T is constant. Everybody's clear on that? So, here's my question. What should I write if P1 over T1 equals P2 over T2? Tell me. What's the P1? 2 atmospheres. What is T1? Say again? Of what? Kelvin. Always remember the temperature in calculations like this must be in Kelvin. So T1 equals 18 degrees Celsius, or if you add 273, 291 Kelvin. And it equals, do we know P2? No, that's what we're trying to find. Do we know T2? What is it? So 335. Everybody's following me on that? All right, all good? Perfect. Yeah, whatever. Calculate it yourself, I don't care. Make sense? So your P2 will be 2 atmosphere multiplied by 335 Kelvin over 291 Kelvin. These units cancel each other out. You can press the buttons on the calculator. Okay. Same story. So P1 T1 equals P2 T2. Therefore, P1 is what? 645 torr. T1. Huh? Yes, which means 401. If my calculations... No.
Yeah.
Yes. Calculations are correct. Okay? And here you have the unknown temperature and the pressure at 824 torr. Right? So the equation for calculating your answer will be 401 Kelvin by 824 torr over 645 torr. My suggestion, hear me out, in general, you do these calculations, always check the units, and before you start pushing the numbers on the calculator, think about the logic. So if you have a pressure of 645 at one temperature, and then you are asked, what should be the temperature to have a greater pressure? Temperature is going to be higher than that.
So it's almost like you're figuring out a proportion.
It is a proportion. It is what you are looking at is a proportion. Okay? Again, we're not going to get through the calculations, but remember this, if you see temperature in degrees Celsius, make sure that whatever your answer is in Kelvin, your final will be answer in Kelvin minus 273. Questions? All right. And the combined gas law, it states it's fairly simple. So when you combine the Boyles, the Charles, the Gay-Lussac, you can say that when N, the amount of gas, is constant, the product of P and V divided by T is the same. Okay, now, hear me out. What this law is intended to do is to provide the way to calculate the parameters in the conditions where more than one of them can change. Okay? For instance, when you just a quick, it's completely off the cuff. You have some kind of a vessel that can change its volume, okay, which contains a gas. So you take this vessel and you start pushing it down in the water. Oh, better yet, you have a vessel, but it doesn't change volume. So volume remains constant, right? You start pushing it down the bottom of the ocean, both pressure and the temperature are going to be changing, okay? If the volume can change as well, then you can figure out what's going to be the volume at the certain temperature and the certain pressure. You see what I'm saying? Like at the depth of, I don't know, 50 meters, there is a certain pressure, roughly 6 atmospheres, and a certain temperature which is different from what you had on the water surface. So this is an example of the calculations like that. So we can say that P1, V1, T1 equals P2, V2, T2. Can we say that? So P1, V1, T1. You with me? P2, T2. We need to find volume that is V2. Clear? So this is what it's going to look like. 646. Do you mind if I'll just write millimeters? We all know that it's mercury, right? Multiplied by the volume, which is 675. Divided by the temperature, which is what? 308. Kelvin. Remember, folks, Kelvin. And then here we have pressure of 802. Unknown volume. Okay? What do you write in the bottom? 178 Kelvin. So, when you do all your calculations, this is what you end up with. 646 millimeters of mercury multiplied by 675 ml multiplied by 178 Kelvin divided by 308 Kelvin and divided by 802 millimeters of mercury. Make sure that the units are cancelled out, units that you don't need, so now you have it in milliliters. Does that make sense? So let's do another one, and then I'm going to tell you something that I find very fascinating. So this is a sort of a tricky question. So what is P1? 0.8. What is V1? And this is T1. Everybody agrees? Now we need to find the temperature, T2. We do have P2 and V2. So I want you to basically tell me what to write here. Go on. Go ahead. 0.8 multiplied by what? Good catch. You see that? This unit is liters. You see that? 0.180 liters. your answer, well, the units for V2 is milliliters. You either go to, liters here or milliliters here. I agree with Melia that this is easier to convert into ml. So, yes, 180 over 302 Kelvin equals, go on. Go on. What should I put on the other side? Huh? 3.20 times 90, yes. That's it. I mean, so again, yeah, we can say that 320 multiplied by 90 ml multiplied by 302 Kelvin divided by 0.8 atmosphere and 180 ml. Whatever the number is, it's going to be in Kelvin. Okay? Does that make sense? And then you take the Kelvin and subtract 370. 273. Okay? We can. So it's 2.62 604 Kelvin. And then you can get,
Just to clarify,
Uh-huh.
multiply, you're not dividing anything, right? You're just multiplying.
Wait.
When you multiply the top, you're not dividing anything from the bottom, right? I don't know if we can do this.
I
It's
am.
all of the top divided by all of the bottom. Okay, gotcha. That was it. That's what I was asking.
Sure.
I mean, if that is right.
Can you ask which line are you referring to?
So like the T2, like when you
The final
yeah, when
thing.
you have to put everything together, like when you're getting that 604, like are you dividing the top from the bottom?
Everything on the top is multiplied
Yes.
and then divided by everything on the bottom multiplied.
Okay.
Good?
Yes.
Go on.
So you multiply the bottom first, and then that answer, that's what you divide by, right?
Say it again.
Sorry. So everything on the bottom, so the 0.8 times the 180, you would multiply that, and then that answer is what you would divide by. Is that what you're saying?
Yes.
Yes? Okay.
Yes. The numbers in this problem are such that I can easily do it without a calculator. But if they would be completely like off the chart, yeah, you just take your calculator, multiply everything on top, it's going to be a number. Everything on the bottom, that's going to be a number. And then you divide top by the bottom. Okay. Now, this is an interesting one. So at the standard temperature and pressure, which is 1 atmosphere and 273 Kelvin, okay, the volume of 1 mole of gas is 22.4 liters. So it can be recorded that if at constant temperature and constant pressure, we add more gas, then the volume will increase. Which is sort of duh, if you think about it. Am I making sense? Inflating the balloon is the best example. Let's say I'm going to give you all the balloons. Okay? The pressure. Is the pressure the same? What is it? Say again? No. You are, like, imagine you are inflating the balloon right now, right at this moment. Hold on. Okay? Right? So, that's the balloon. Alicia, you doing it right now. Like, this is you. What's the pressure? I want a number. You are doing it here in this room. What is the pressure in this room? One what? One atmosphere, right? It's an atmospheric pressure. Make sense? What is the temperature? Ballpark is fine. Well, science, 21. Okay, let's make it 21. So temperature is 294 Kelvin. Agreed? You keep inflating, so you add more air, more gas into that balloon. What's going to happen to the size of the balloon? It's going to become bigger, right? Because this is N1 and V1. Okay? Now, when the balloon size increases, what is the pressure? One atmosphere. Does that make sense to everybody? Say again? Because this is where it is. Okay. Let me write this down, and I will try my best to explain why we are saying that. Yes, go ahead.
So, if you were to, it just all depends on the environment that you're blowing the said balloon up in, basically. So, if it were surrounded by water, it wouldn't be as expanded. It would just be like.
Absolutely. Why it wouldn't be as expanding?
Because of the pressure of the water pushing down on it.
But you have to understand something. It sounds very counterintuitive, but imagine you inflated a balloon, tied it up. You don't put any more gas. There is certain volume. It's in this room. Temperature is the same. What is the pressure outside of the balloon? 1 atmosphere. What is the pressure inside of the balloon? Nope. 1 atmosphere. Because, folks, you can interpret pressure as literally like pushing on something. If you have a balloon,
Isn't there pressure pushing on the balloon to keep it bigger than it?
it's not bigger. The volume is the same. Hear me out. The volume is the same. This is your inflated balloon that is tied up. Okay? It doesn't change volume. Do you agree with me? So, volume is constant, correct? Temperature remains the same, and at this point, N is constant. The pressure inside and the pressure outside have to be equivalent. Because if they're not, for any reason, if the inside pressure is greater, it will be expanding. Let's say you're heating up that balloon. If the pressure on the outside is greater, it will be collapsing, like you're cooling it down. Or you poke a hole. When you poke a hole, gas starts to leave the balloon. So N is not constant anymore. The elegance of this is that it can be described in very simple mathematical terms. Okay, does that make sense? So, in case of Avogadro's law, it's pretty straightforward. So 0.75 moles over 1.5 liters. Well, you actually can go either way. Classically, it's 1.5 liters per 0.75 mole. So it's V1 over N1. It has to be the same as 1.2 liters over N2. Make sense? So N2, 1.2 liters multiplied by 0.75 moles divided by 1.5.
You said that was 1.2 liters, but in the problem it says 1.2 moles.
Oh, sorry, my bad. I mixed up. I didn't read the moles correctly. I thought it's liters. So then it's going to be different. Thank you for catching this. 1.2 moles, and that's V2. It will obviously change the equation. So V2 is going to be 1.5 liters multiplied by 1.2 moles divided by 0.75 moles, and that's going to be 2.4 liters. Sounds fair? So standard temperature and pressure, STP, 273 Kelvin, 760 millimeters, 1 atmosphere. Okay? Just to make it clear, a bunch of nerds that are called chemists and physicists, they got together and they're like, what are we going to choose as a standard temperature and pressure? Well, pressure is very obvious, but in terms of temperature, what do we need? 273, 278, which is considered 25 Celsius. What? Let's do 273 because it's easy, it's 0 Celsius, it makes sense. That's it. There's no particular sense to it, except for the fact that if you will account for temperature and pressure, you can calculate that 1 mole of gas occupies 22.4 liters of volume. You should ask a question. What gas? And the answer is any. This is what still, like, I learned that 30 years ago in high school, okay? More than that. And since then, I admire that law of nature. It's so counterintuitive to think that 1 mole of oxygen, of chlorine, of nitrogen, of fluorine at the same temperature and the same pressure will have the same value. Does that make sense? Here, no difference. Now, we're going to do the, learning check, and we're going to do fairly quick. So, read the first problem. What do we need to do with 4 grams? Of methane? What do we need to convert grams into? Moles. Remember, mass is useless to a large extent in chemistry. Moles are the kings, okay? So in order to go from grams to moles, what should I put at the bottom? And on top? What is the molar mass of methane? Carbon's 12, hydrogen's 1, So 1 carbon is 12, right? 16. So molar mass of CH4 is the molar mass for carbon, which is 12. Questions? No? Plus 4, which come from hydrogens. So that's 16. Right? And then you need to do another conversion factor. You need to go from moles to liters. What is the volume that 1 mole of a gas, 22.4, occupies at those standard conditions? Okay. That is. Well, the Avogadro volume. Okay, you're asking if I will give you the information that 1 mole of a gas occupies 22.4 liters at standard temperature and pressure. I gave it to you. You're supposed to remember that. Okay, but it's one number, 22.4. So yeah. Yeah, 560, yes. You can do the calculations. Okay? And now regarding helium, here's what you need to do. So you have 8 liters, right? You have to go from liters to moles first. So what's going to be on the bottom of that fraction? So you have 1 mole. What is the volume of 1 mole of gas? 22.4 liters. Good. Now we have to go from moles to grams. So how much does 1 mole of helium weigh? 4 grams. I mean, 32, yeah, this one. Because we end up with 32 over 22.4, and it's, yeah, like 1.43. Does that make sense? Before we proceed, I wanted to go all the way back to, not here, no, this. Okay. So this is entirely just to marvel on things. Scientists can achieve really low temperatures, like fractions of 1 Kelvin, super close to 0 Kelvin. The first person who actually broke that 1 Kelvin and almost got to 0 was a guy in Netherlands in Leuven University, and he got the Nobel Prize for it, basically. Kamerlingh Onnes. Okay, anyway. How do you do that? Like, you're not sticking gas in a fridge. The answer is on the screen. So we figured that if temperature goes up, right? Okay, if the temperature goes up, the volume goes up. Well, you cannot just start squeezing gas. Instead, you're going to reduce the amount of gas in the closed chamber. You're going to start sucking it out. Okay? Eventually, because of the reduced amount. And you also can expand the volume. The temperature will go down. So they essentially were creating more and more vacuum in a special chamber. Go ahead.
I thought the combined gas law was only valid if N was constant.
Right, but
But
it's
really long.
so you're not violating the law. You just can't apply that equation anymore. Okay, it becomes complicated. In other words, what they did, they kind of suck out the gas out of a chamber, and that reduces the temperature in the chamber. Have you ever used disposable propane canisters for like camping stoves? No? Well, sure. We did. So when you plug in that canister into the stove and open, and start and fire up the stove, the propane leaves the canister. The volume of the canister does not change, but the pressure and the temperatures, it's not just cold. If you run it long enough, it's going to start freezing. You can be camping in the summer, and this canister, if it runs for a long time, it is frozen. There's like snow on it. So this is what they did. This is how we get to those super low temperatures. By basically creating some artificial conditions, we can suck the gas out of the chamber.
Will all of the gas laws be provided on the exam?
No. The relationships, yes, you have to remember. So yes, I don't think there will be questions that are like, what is Boyle's law? But rather, you have constant temperature and amount. At the volume X, there was a pressure Y. What's going to be the pressure and the volume Z? Am I making sense? Yes, you will have to do the calculations, but again, it's multiple choice. Oh, yeah. I mean, it's a rule for, I told you, I'm not providing this, but every time you take an exam, except for the final, you have one index card, both sides. For the final, 2 index cards, both sides. Final is comprehensive, therefore 2 index cards. All right. So partial pressure is a very simple concept. If you have a mixture of gases, the individual pressure that every component of the mixture exerts is proportional to its concentration in the mixture. So here, you have 2 gases, helium and argon. Helium, if we take only helium atoms, it produces the pressure of 2 atmospheres. Does that make sense? Argon, if we only take argon, produces the pressure of 4 atmospheres. Together, they produce a pressure of 6 atmospheres. Now, how many, it's a hypothetical, how many helium atoms do we have? 4. How many argon atoms do we have? 8. So the amount of argon is 2 times greater than the amount of helium. So the partial pressure of argon will be twice as much as the partial pressure of helium. Okay? So if you take a bunch of gases and add them together in the mixture, So best example, and I want to do it before we get to actual conversation about the air. So what is the atmospheric pressure? Let's do 7. Okay. 1's fine. 1 is even easier. You with me? What is the percentage, molar percentage of nitrogen in the air? You know the answer. 79%. So 79%. So 0.79 atmospheres. Make sense? What is the percentage of oxygen? 21, no, 22. No. 20, a little less than 21, but for intents and purposes, 21, so 0.21 atmospheres. Does that make sense? If you replace it with millimeters of mercury, I can't do it for nitrogen, but I can fairly easily do it for, what's the word? Oxygen, yes. Thank you very much. So it's going to be 159.6 millimeters of mercury. Oh, 760. Okay, does that make sense? So you can mix different gases in different molar ratios. Okay? That makes sense? But, for instance, if the amount is 1 mole, then the volume is going to be always 22.4 liters, whether it's a mixture or pure gas. And the pressure is going to be 1 atmosphere. Okay? This is the illustration of the concept. So this is the percentage, molar percentage of nitrogen. This is its partial pressure. This is the molar percentage of oxygen. This is its partial pressure. Does that make sense? Okay, now, how is that relevant? Let's talk about carbon dioxide, shall we? A little bit. So let me ask you this. If you have a mix, can you express the concentrations of each component in percentages? All those percentages, what do they add up to? 100, right? Everybody agrees with that? So if I would start increasing the proportion of CO2 in this room, what would happen to the relative concentration, the concentration of nitrogen and oxygen? It would decrease. Does that make sense? And it means that you breathing the mix, but the percentage of oxygen, and therefore partial pressure of oxygen, goes down. Okay? Am I making sense right now? Let's say I'm going to increase.
So basically diluting the other.
Exactly. But why is this important? Many of you are going into nursing. Anyone goes into respiratory therapy? Okay. You go into nursing. What drives oxygen from the lungs into the blood is the pressure difference. Partial pressure of oxygen in your lungs is greater than the partial pressure of oxygen in your blood. Does that make sense? When you start decreasing the partial pressure of oxygen, it gets harder to deliver oxygen in your blood. So people become hypoxic. Am I making sense? Now, here's another illustration of that important concept from the sort of clinical perspective. I don't remember how does pressure change as you go up. Let's say you are very, very up in the mountains. Okay? Remember, this is a partial pressure at the sea level. This is like what you strive for. Okay? You're up in the mountains. The percentage of oxygen doesn't change. I want to highlight it. All right? The percentage is the same, 21. But you are so up in the mountains that the atmospheric pressure there is 400 millimeters of mercury. Are you with me? So what will be the partial pressure of oxygen then? No? No? Okay, let's go back here. Let's work on this. Pressure depends on total number of particles, fine. Total pressure, the sum of partial pressures of these gases. But each partial pressure is proportional to the share of this gas in the mixture. Are you with me? Sorry, Alicia, you are pretty much the only person who actually tells me, no, I don't get it. Well, Kaylee does it too. But don't hesitate. I really want to hear, no, I don't get it. So I'm going to talk to you. What is the share of oxygen in the air? 21%. Here in this room. What is the share of oxygen in the air on that mountain? Nope. So, okay. Let me start over.
So would you have to raise all the other gases too, or
erase it. Erase what I said. Let's start over. What is the atmospheric pressure at the sea level? 760.
That's what we were talking about earlier that she asked.
760 here. What is the share of nitrogen? 78.2%. So we can say that the partial pressure of nitrogen equals total pressure, atmospheric, right? Multiplied by its share, which is 78.2%. You can do calculations, it comes down to 594. Does that make sense?
Why at the bottom do you have the pressure of atmosphere is 400? Maybe I'm jumping the gun.
You're jumping a little bit.
Okay.
Does that make sense?
Yes.
The logic that we followed so far. Good? Okay. So this is the composition of air at the sea level. Fraction-wise, share-wise, does it change when you go up in the mountain? It does not. Percentage-wise, it's the same. But the total pressure, the atmospheric pressure, is going to be lower. So, in the mountains, like you are on top of Mount Denali. I don't know. I really have no idea how high you have to go. You have 400 millimeters of mercury. Are you with me? How do we calculate then the partial pressure of oxygen?
so we would have to create another proportion like we did with the other.
The partial pressure of a component is proportional to its share. So this is total.
Like 21% of 400.
Yes, 21% of 400. Does that make sense? No. 21 is this. This is just, 21 is this. Does that make sense? So I don't have an analogy to it. I don't. Okay, actually I do. It sucks, but I think it's gonna work. So let's say the percentage of Asian students in the university in Ohio State is 20%. You can take the entire Ohio State, 56,000 students or whatever, and 20% of them are going to be Asian. You can shrink the size of the sample but still make it random and take 20,000 students out of Ohio State randomly. 20% of them are still Asians. Same idea here. Okay? So what I'm getting at is that the partial pressure at this point is 84 millimeters for oxygen, which is considerably less than 160, which means it's much harder to drive oxygen into your blood at that elevation. Does that make sense? Like if you would jump with like the parachute out of a plane that flies 36,000 feet, roughly 10 kilometers, even if you will be dressed super warm, you probably will suffocate because it's so rarefied. I don't know if you've heard about some dude from Europe who did the highest jump in the history. Like he had a little balloon that got him to 70-something kilometers. So he was technically in space. And he jumped from there. He was jumping with oxygen tank. Like there is atmosphere, but the pressure is so low, he would die. Okay? That makes sense to you. So, there you go. Oxygen pressure is 0.450 atmospheres. Helium pressure is 855, millimeters. Right? Can you add those numbers together? Yeah. So basically you can say that the total pressure is 855 plus 0.450 atmospheres. I use conversion factor here to just illustrate my train of thought. Whatever the number is. Okay?
Could you go back to
Always stop, thank you, always stop me if I'm going too fast. Okay? This number should be 342. And at the end of the day, it's going to be 1097. You can shame me if I did the calculations wrong. Okay. Good? Okay. So, God's sakes. All right. What would you do here? Look at this. Total pressure is 8 atmosphere, which we can immediately convert into millimeters of mercury, right? It's going to be 62 40. Okay? Yeah, 760. Yes, it's going to be 608. Is that better? I think so. Yeah, it's 760. Right?
That's it times.
So 8 atmospheres times 760 millimeters of mercury gives you this number. Okay? All good? I'm getting like overexcited about this. And this is why I'm skipping steps. Good? So we can say that the total equals the pressure of helium plus pressure of oxygen. Therefore, pressure of helium is total pressure minus oxygen. Therefore, pressure of helium equals total is what? 6080, right? Oxygen is 1280. And that is going to give us 4800 millimeters of mercury. Questions? Arithmetic, folks.